Two compounds, X and Y, involved in a chemical reaction. The amount in grams of these compounds, T minutes after the reaction starts, are X and Y respectively, and they're modeled by these differential equations, first order. However, they are coupled equations. The rate of change of X depends on Y, and the rate of change of Y depends on X. And we're asked to essentially combine them appropriately to get a second order differential equation of X, just in terms of time, no Y's in there, and then we'll be able to solve it. Sounds good. So what we're going to do is we're going to take this equation here and we're going to differentiate both sides with respect to t. Then we'll get d2x by dt squared equals minus 5 dx by dt plus 10 dy by dt. And the minus 30, of course, goes. Now I can replace that dy by dt by this. So it's going to be plus 10 times minus 2x plus 3y minus 4. And let's just expand the bracket. So minus 20x plus 30y minus 40. Okay, we're not quite there, but we are nearly there. And it works similar every time with these sorts of questions. So now I want to get rid of my y. But how to do that? What I can do is return to here and write 10y equal to dx by dt plus 5x, then plus 30. Just rearranged it. And that means 30y is going to be 3 dx by dt plus 15x plus 90. So back down here, we're going to get minus 5 dx by dt minus 20x plus 3 dx by dt plus 15x plus 90, and then don't forget the minus 40. So that will give me minus 2 dx by dt. I'm just combining like terms here. Minus 5x plus 50. And finally, that means that d2x by dt squared plus 2 dx by dt plus 5x is going to equal 50 as required. And you know where this is headed. We're now asked to find a general solution for x and then for y. And then we've got the particular solution to look for. So to begin with, we're going to look at the complementary function, and that is when we set this equal to 0. And then we'll look at the particular integral for when we get the 50. So we let x equal a e to the kt as our trial function, put it in, and it gives us our auxiliary equation, because we divide through by it after differentiating this function, and we get k squared plus 2k plus 5 equals 0, of course. So I've not gone into detail on that there, but that is our standard process. And you can either use a quadratic formula. In this case, it's going to be quite quick to complete the square. It's not going to factorize, by the way. We're going to be getting complex solutions. So k plus 1 squared is actually going to equal minus 4, which means k ends up being minus 1 plus or minus 2i. This gives us, by the way, e to the minus t times e to the minus 2it, and e to the minus t times e to the 2it. But you can use Euler's relation and write that one as in terms of sine and cos. And you're going to get sine 2t and cos 2t. They might just be negative, and they're similar here. But we don't use that approach. What we can actually then do, I'm not going to go into lots of detail on it here, but we've got e to the minus t for both. And then we get our arbitrary constant times sine 2t plus another arbitrary constant times cos 2t. That's our standard process for dealing with this. In other videos, I explain where that comes from, because there's so much going on here, I don't think I'm going to. that's our complementary function. Right, now we've got our particular integral. So what we do for this is take a look at the right-hand side, and we're just going to use a little trial function, and it's just going to be a constant. Like if you try and let it equal a function of t, then you're going to get, because there's an x in there, you're going to get a function of t on the left-hand side, but none of these are going to have a t in it, and you're just going to get the coefficient equal to 0. So because it's a constant, we just go with a constant. Let's x equal, what should we call it? I've already used k, so I'll call it lambda. And then dx by dt is just going to equal 0. So this is very quick to find, because that's 0, that's 0. I'm just going to get 5 lambda is 50. So lambda will equal 10. And therefore my x particular integral is actually 10. I need to add that for my general solution. So the general solution is e to the minus t, a sine 2t plus b cos 2t plus 10. That 10 is needed to give us the 50 on the right-hand side. Right, that was to find our general solution for x, now to find a general solution for y, but we do not need to solve another second-order differential equation. We have this right here. Y is related to the derivative. It's only 3 marks, so there's still quite a lot of work to do in places where we can make mistakes. So I'm just going to rearrange this. 10y is going to be dx by dt plus 5x plus 30. Right, we know what 30 is. We've got what x is. We need dx by dt. So let's differentiate. Got to use the product rule here. So I'm first of all just going to differentiate the e to the minus t. I'm going to get minus e to the minus t. And then this is going to stay as it is. The 10 disappears. And then it'll be plus e to the minus t times the derivative of this bit. Now, when I differentiate sine, I get cos, but I'm going to bring a 2 down, and cos is going to become minus sine. I'm going to bring a 2 down, so I'm actually going to factorize that 2 out, and then I will get a cos 2t minus b cos 2t. And then I want to like combine this. I've got the e to the minus t here. Do you know what? I kind of regret. I should have just kept the 2's inside. Okay, so now I've factorized my e to the minus t out of everything. I'm going to get 2a cos t minus b. So it'll be 2a minus b cos 2t. And then I've got minus 2b e to the minus 2t and a minus a. So it's going to be minus a plus 2b sine 2t. And that means 10y is going to equal this thing that I've just found. I'm just going to copy and paste it actually. Plus 5 lots of this. So it's going to be plus 5 times this plus 50, and then plus 30. Okay, what I can do is times this by 5 and this by 5. I think that'll make it easier to combine. So we're going to get e to the minus t. Right, let's look at the cos part. I've got 2a minus b cos t, but now I'm adding 5b. So it's going to become 2a plus 4b cos 2t. And I've got minus a minus 2b sine 2t, but I'm adding 5a, so I'm going to get a plus 4a. So actually it will become plus 4a minus 2b sine 2t. Okay, when I did that originally, I actually made a mistake. It's so easy to just like not quite like accidentally combine the causes with the sines, etc. And then I'm adding 80. Okay. Oh, I personally think this is like more effort than solving the equation to start with. And that's like, that's kind of tried and tested. This one here is just, yeah, awkward. So we're nearly there. The y general solution, just need to divide through by 10. We're going to get 1 over 10 e to the minus t and all of this. And then divide that 80 by 10, so we get a plus 8. Okay, now we're given initial conditions and we're asked to find a particular solution for x and for y. Okay, let's bring down the general solution for x. We've already got it for y right next to us. And let's sub in. So 2, let me do this in blue actually, 2, I'm going to substitute in here, is going to equal e to the 0, which is just 1, times e to the sine 0, which is just 0, plus b plus 10. So actually I get 2 equals b plus 10. B is equal to minus 8. Ah, sorted. Then just need to sub in y equals 5. So 5 is going to equal 1 over 10 e to the 0, that's just 1. Then I am going to get 2a plus 4b times cos of 0, that's just 1. And the sine 2t again is going to disappear. And I've got plus 8. That means minus 3, just minusing the 8 here, is going to equal 1 over 10 2a minus 32. So 2a minus 32 is going to equal minus 30. 2a is going to equal 2a is going to equal 1. Hey, we found both of the constants. And that means my x general solution, yeah, should I fit it in here? No, sorry, x particular solution is going to equal e to the minus t sine 2t minus 8 cos 2t plus 10. Quite fit in, could I? And then y particular solution is going to equal 1 over 10 e to the minus t. Right, now I've got to do 2a plus 4b. So that's 2. And then remember, b was minus 8, so 2 minus 32, I'm going to get minus 30. Just realized that should have been a 2t as well. I lost that. And then 4a minus 2b is 4 plus 16. I'm going to get a plus 20. Okay, and we can make this neater now. So y particular solution is going to then equal e to the minus t 2 sine 2t minus 3 cos 2t, because I've just divided through by 10, and then plus 8. Well done, you're doing great. Very last part. A scientist thinks that the chemical reaction will have stopped after 8 minutes. Explain whether this is supported by the model. So what I did is I worked out the values when t was equal to 8. And for x, we get 10.002. You sub in, and y is equal to 8.000. And then I said, as t approaches infinity, x is going to approach 10, because this term here is going to approach 0, because we've got a negative exponential going on. I know it's going to oscillate, but that is going to dominate. And y is going to approach 8. So they're very close. So I just said, yes, the reaction um, has, it hasn't exactly stopped. It's still going to be like decreasing a little bit, but it has essentially stopped to all purposes. So I think I get the mark for that. Let's just compare what the mark scheme do. They actually don't do any calculations. They just said when t is greater than 8, the amount of compound and the amount of compound y remain approximately constant at 10 and 8 respectively. They're using this idea here, I guess. But they haven't really, I don't know, I feel like we should actually substitute in just to check. I know it's a negative exponential. It goes to 0 really quickly. But still, I prefer how I did it. But yeah, which suggests the chemical reaction has stopped, and this supports the scientist's claim. Right. Well done on this question. Feels like it's been an epic one. A lot of calculations. Nicely done.